So today what I'm gonna talk to you about is decoding lights from exotic worlds, meaning how are we gonna learn about exoplanets from the light that we receive from these objects, because essentially they are so far away that we cannot go there like we can go on planets from the solar system. And so what I will show today is what are the tools that we can use to explore these worlds from our planet. So in order to understand how we can explore these worlds outside our solar system, I think it's interesting to see, what are the images, what are the ways we see the planets inside our solar system. And generally, the first images that we got from very exotic worlds are like these ones, where we see Jupiter. And nowadays, of course, we have better cameras, better equipment. And for example, if we look at footage from the Juno mission, we have something like this. And so, of course, when we imagine other planets, we really see objects, extended objects, with what we see here, clouds, winds, structures in the atmospheres, and bands, colors that are different, for example, from the equator to the poles. And the question that we can ask ourselves is, really, can we image exoplanets? Because we see a lot of these illustrations here on the web, and we kind of see that these are artist illustrations of these exoplanets. But really, the question remains, would we be able to do such images of exoplanets? So let's try to see, if we can do that. And to have an idea, I think it's important to have in mind what are the length scales of the problem. So here, you have kind of a view of the solar system. So with all the 8 planets and the minor planet Pluto. And just to have an idea, we know that the distance from the Sun to the Earth is about 1 astronomical unit, and so the size of the solar system is about 10 to 100 astronomical units, depending how you define exactly the solar system. But just to give you an idea, that means 1 to 10 billions of kilometers. But the nearest star, and we know that exoplanets are around other stars than the Sun, the nearest star is about 4 light years away, which means 250,000 astronomical units, and what we call also 1.3 parsecs. So this is really enormous, and it's very difficult to get our mind around this. So let's just try to put some other numbers on this. So if the Sun was a ping pong ball of about 4 centimeters, Jupiter and Saturn would be ladybugs, about 4 millimeters, and they would be at about 20 and 40 meters from the Sun. The Earth would be even smaller than that, because the Earth would be the dot on the spot on the back of the ladybug. And actually, you can see it because, for example, the size of the small red dot that we call the Great Red Spot on Jupiter is about the size of the Earth. So you can really see the scale of this. The problem is that the nearest exo-Earth with this scaling would be more than 1,000 kilometers away. We kind of feel from these numbers that it's going to be really difficult to image an exoplanet. But can we quantify how difficult that would be? So for this, we have to understand a bit there are a few limitations to imaging other planets or imaging objects in general. And the first limitation is really what we call the diffraction limit of the telescope. So it's basically due to the fact that light is not it's photons, but it's also a wave. And so because it is a wave, when it's going to enter the telescope, there will be a process that's called diffraction that will tend to change the path of the light, and so it will change the image that we see from the source. So for example, here if we look at the distant star, and it emits some light at a wavelength lambda, and it's received by a telescope of size d, diameter d, we would imagine that the image that we have of a star and a planet are exactly like here. So two small dots, one being, of course, smaller than the others. But the problem is that if we have diffraction, the image that we're going to see is going to look like that, and that's called an airy pattern. And just because of the light of the stars is diffracted by the telescope, and it's dispersed over different parts of the image. And of course, on the image on the right, we cannot see the dot from the planet. And the problem is that this dot is hidden by the diffraction spot of the star. So what we need to do to actually see this planet is have a planet that is further away from the star than it is here. And so if we move the planet slightly away, we can see that now we can see the difference between the spot of the star and the spot of the planet. So to give you an idea, the size of this diffraction pattern is typically, in terms of angle, lambda over d, so the wavelength divided by the diameter of the telescope. And so it means that for an 8-meter telescope, which is about the biggest telescope that we have on Earth at the Very Large Telescope Array, VLT. And if we observe in the visible or near infrared, let's say 1 micron to make the computation simple, then lambda over d is really a very tiny angle, 0.02 arc seconds. But still, if we translate that at what this angular size means around a star that is at 4 light years away, meaning the closest star to our sun, then an 8-meter telescope would be able to resolve an object that would have the size only of 400 times the size of the Earth, 4 times the size of the Sun, or 3% of the Earth-Sun distance. So what it means is that if we have this 8-meter telescope looking at the closest star, we could see a planet if it were orbiting at the distance from the same distance from its star than the Earth is orbiting from the Sun. But still, this planet would be a dot, meaning that we could not. At the moment, it's completely impossible to image a planet the same way that we image the planets in our solar system. The problem is that even with this, even if we are able to resolve, meaning that the two spots will not be the same on our image, there is a second problem, and the second limitation is contrast. Because if you look at any random bright star in the sky, and you take an image, here is what you see. And you see that the problem is that the star is so much brighter than the planet that the planet, even if it's far away enough, it's going to be drawn in the light, still in the diffraction light from the star. And the problem is here because if you try again to look at this airy pattern, but you show, for example, what is the intensity of this light as a function of the distance at which you look from the star, you see that you have this pattern. So you see the intensity of light that is decreasing as you get away from the star. The problem is that if you put the real intensity or the contrast of for example, the Earth and Jupiter in this diagram, for a planet like as if it were seen at like 10 parsecs away, you would have something like this. So basically, even Jupiter is so faint that it's completely impossible to see it because the star is so bright, and the contrast between Jupiter and the star, or even the Earth and the star, is really huge, and you cannot see it. So the only way that you can do that, for example, well, there are ways to resolve this problem. One way is if you have a planet, you can put it in between you and the star and the other planet that you want to look at. And for example, here you see that thanks to that, the star from the Sun is blocked. This is an image from Cassini, for example, looking at Saturn and the Sun. And you see that there is a small dot here, and this small dot is the Earth. And so that's really what we think. It's really simple. you just hide the star and look at the planet that is just next to it. The problem is that it's not really practical, to come up with to build a whole new planet each time you want to look at a different exoplanet. So what we have tried to do is to come up with another way, an artificial way to do exactly the same. If you look inside the telescope, you have, for example, on the diagram in the upper part, you can see that on the left the light is coming in and is focused on the focal plane. And you see here the pattern of the same pattern, the light of the star. And what you can do is just here at the center, where you have most light from the star, you can just put what we call a Leo stop. The name comes from Bernard Leo, who developed this in the 30s to actually look at the corona of the sun without eclipses. And when you do this, you actually block the starlight, and you see that the light in the image goes way down, as we can see in the lower diagram. And so the contrast of the objects that you can look at next to the star is much better. For example, here is what a star would look like if you looked at it without coronagraph, and you see all these diffraction pattern. You see also this cross, which is due to the diffraction of what we call the spiders, which is what is actually maintaining the secondary mirror in a telescope. And when you try to remove that and you put a Leo stop to actually remove the light from the star, you get something like this. There is much less intensity from the starlight in the middle, and you can now see on the right of the star, you can see a little dot, which is probably an object that has a very faint contrast, but that you can see thanks to this device. You see here that the problem is that the contrast, if you look at the lower curve on this diagram, is still not 10 to the minus 10 or 10 to the minus 9 that we've seen for the Earth and Jupiter. And so what it means is that even with this, the current kind of coronagraph that we have, we cannot yet image the Earth or Jupiter. So, but did we observe some things? Fortunately, if you look at the physics of stellar and substellar objects and planets, fortunately, many planets are much brighter than the Earth. So here, for example, there is a diagram of the luminosity of different objects. Each curve is an object of a different mass, divided by the luminosity of the sun. And the bottom axis is time. So you get from very early ages at the left, and then you get to the age of the solar system to the right. And the curves that you have at the top are from very low mass stars in blue. So the upper curve is about 0.2 solar mass, so 20% of the mass of the sun. Then you have in green what we call the brown dwarfs, which are objects that are a bit less massive, not massive enough to burn hydrogen and so to be called stars, but a bit too massive to actually be called planets. And so we go basically from 0.08 solar mass, so meaning 80 Jupiter masses, down to about 12 Jupiter masses. And then in red, we have what we would call the super Jupiters, so between 12 and 1 Jupiter mass. They are in red. And what you see is that their luminosity, well, it decreases over time because as they are young, as they are formed from accretion. And so all this infalling gas is heating the object. And so it has to release this primordial energy. And then you have two scenarios. Either you're a star and at some point you're in blue, so meaning that your luminosity hits a bottom threshold because you ignite hydrogen fusion, and so your luminosity stops decreasing, you are in equilibrium, and you live your life. Or you are a substellar object, and then you just keep cooling over time, and your luminosity decreases. But what is important here in the context we're talking about is that if you look at the contrast on the left, you see that this contrast is much bigger than 10 to the minus 10. Actually, for many of these objects, it can go to 10 to the minus 5, 10 to the minus 4, which is about the contrast that we've seen in this diagram here. So meaning that if we look at massive enough objects or at objects that are young enough, we could observe them. And effectively, we did. So this is an image of the beta Pictors system. So basically what you see here is around you see an image where you have the disk of the star, the circumstellar disk, because this is a very young star that still has a gaseous disk around it. And then what you have in the middle is a coronagraphic image of the star with the planet around it, the small dot that you see, which is beta Pictors b, which is a super Jupiter. And here, for example, the luminosity of the planet is only 10 to the minus 4, about 10 to the minus 4, compared to the luminosity of the star. And that's why, with the current coronagraph, we could image this planet. Another very famous example is this one, HR 8799, where we actually see not one, but 4 planets that are around the star that has been allowed by these coronagraphs. And what is interesting here is that you can see that because we are able to observe these planets not only at a single time, but we can come back year after year, then we will see that these objects, they move over time just as we see the planets moving around the sun. And so that gives us additional information on those planets, because it means that we kind of have an idea of what is the orbital period of these objects. And so we kind of know, we have more information about the distance from the star, the mass of the star. And so with all this information, we can start to get an idea about the structure, the internal structure, the mass, and the age of these objects. Thanks to this diagram, we can actually show, we can see, because we measured for these planets, we measured what is their luminosity compared to the star, and we now know that these planets, for example, they are in this region that is shaded in blue. And so we know that the planets that we observed through this method are mostly, as I said, either planets that are more massive, much more massive than Jupiter, but they also have to be very young. The problem is that there are not that many young planets around it, around us. And so that's why with this method, we only, to date, we only image dozens of planets. And so they are all young and massive. And the question is, well, okay, that's great, but well, maybe you have heard that we have discovered, thousands, even more than 4,000 exoplanets. So the real question is, how did we do that? And of course, it's not thanks to direct imaging, because as I said, direct imaging is a very challenging field. So now, how did we do that? So we're going to move to 2 different techniques that really were, well, actually, even historically, were the first used to actually find these objects, but have been much more useful in the sense that allowed us to discover a much bigger number of planets. So the first one, historically, is what we call radial velocimetry. So the idea is really simple. What is less simple to understand is that this technique, and the technique I'm going to show you after, is actually indirect, in the sense that we did not actually collect light from the planet. We actually collect light from the star, but because of some properties of this light, then we're going to infer the presence of a planet. And we'll see how we do that. So for radial velocimetry, the main idea is that when you have a planet orbiting around a star, then we always say this, a planet orbiting around a star. But actually what is happening is that we have a planet and a star orbiting around the center of mass of the system. And because the planet is much lighter than the star, the planet does a much bigger motion, but the star still has some motion around this center of mass. So because there are different atoms and molecules inside the star, These atoms and molecules, they have what we call spectroscopic lines. They're on the dark lines in the spectrum that we see here. And these lines, they have wavelengths that are very well studied and measured in the lab. Now, if you observe a star, because the star moves, the wavelength of this line, they will appear to shift during the motion of the star. And it's exactly when you hear, for example, the sirens in the street. If you hear the siren of a police car, for example, coming towards you, the sound of the siren will have a higher pitch, and then will move away from you, the sound of the siren will have a lower pitch. That's what we call the Doppler effect. And the Doppler effect works with sound, but it works exactly the same with light. And so here, when the star is going away from you, the wavelength at which you will see the lines of the atoms inside the star will be a bit longer, meaning you will see the star appear a bit redder. And when the star is coming towards you, then the light will appear a bit bluer, and these lines, they will be shifted at shorter wavelength. And so when we observe a star at our telescope, we can compare the wavelength of these spectroscopic lines with the wavelength that is fixed in the frame of the laboratory. And if we see a motion that is moving back and forth like this, we can know that this star is actually undergoing motion due to the presence of a planet. And that's how we measure this distance, the radial velocity, so the velocity of the star away or towards us. And then, with the current precision that we have with this method, with the current spectrographs, is about 20 centimeters per second. So we can measure the motion of a star of about 20 centimeters per second. So now, if we try to compute what is the motion that the Earth imprints on the Sun, we see that it's only 9 centimeters per second. So it's really hard, it's actually impossible for the moment to observe, to measure the motion of the Sun due to the Earth. But if we look at the motion due to Jupiter, because Jupiter is much more massive, it will imprint a much bigger motion on the star. And so the motion induced by Jupiter and the Sun is about 10 meters per second. So actually we can measure this. The difficulty, of course, is that with this method you have to wait a full orbit to see the whole sinusoidal variation of the wavelength of the spectroscopic lines that occurs during a full orbit. What this means is that if there were only Earths and Jupiters like our own around other stars, it would have been very difficult to discover them. But of course, that didn't stop people trying to actually measure and detect these planets. And they were lucky enough that actually many of the Jupiters out there are not like our own Jupiters. They are hot Jupiters. They are Jupiters that have migrated by some process very close to the star. And here, for example, is a diagram showing the velocity, so the radial velocity of a star, which is 51 Pegasi, as a function of time. And you see that you have this sinusoidal variation of the radial velocity with time, with a period of 0.2 days and a semi-amplitude of about 50 kilometers per second. And when you see that, it means that you have a planet that is orbiting its star every 4.2 days about, and that has a mass it doesn't have to be much greater than Jupiter, because actually, as you see, the semi-amplitude is proportional to the mass of the planet, but also inversely proportional to the distance at which the planet is from the star. And so here, because the period of the planet is much shorter, it means that this planet is much closer to the star, and so that's why we have such a large amplitude of 50 kilometers per second of this motion. And so this actually is the discovery of the first planet around a solar-like star, around this star that is 51 pKc, and that's what got the Nobel Prize for Michel Mayor and Didier Queloz for this. Well, the Nobel Prize was a few years ago, but the discovery was in '95. This discovery is actually very important because it's really what launched the whole theme of exoplanet forward. Because before that, exoplanets were, many people thought that they were there, but that's really at that point that we knew it was a fact, and that since then many discoveries were triggered, and that's why now exoplanets are a big part of astrophysics. And if you look at all the planets that have been discovered by radial velocity, you see that nowadays a lot of them have been discovered this way. Here I have a diagram where you see the mass of the planet on the left and the semi-major axis on the bottom. So, and you see all these planets that have been discovered this way. So you have a small clump on the upper left of the diagram. These are these hot Jupiters that I was talking about. So with a mass close to 300 times the mass of the Earth, which is about the mass of Jupiter. You see actually where Jupiter is in this diagram on the right. You have another clump close to Jupiter, which are actually what we call regular or cold Jupiters that have been found. They have not been found in the beginning, but now they have been found because the surveys could look for them for many years, and that's how we got to measure their orbital motion, even if there are several AUs from their star. And you see that there is a lot also of objects with smaller mass. The problem is that actually, as you see from the red dashed lines, you can see the limits of what we are able to measure right now. I told you about 20 centimeters per second, so that's close to the lowest red dashed line. And you see that actually, as you could expect, we didn't discover any planets below this line because these planets are either so far away from the star or so light, not massive enough, that the motion of the star is not big enough for us to discover them. And the problem is that, as you see, the Earth is in this region. So, as I said, we could not today discover the Earth around a solar-type star with this technique. The other problem with this technique, which still allowed us to discover 500 to 1,000 planets, is that it's very time-consuming, because even nowadays we still need to take spectra of stars at random to discover a planet, but we need to take the spectra for a long time, sometimes several years, without knowing whether there is a planet there, and we need to take spectra for these stars one after another, and so it's really time-consuming, because you cannot look at many planets at once. You always need to look at these planets one after another. So that's why it's actually not nowadays, it's historically the first technique that allowed us to discover these planets, but it's not where most of the planets that we've discovered now come from. Where they come from is from transit photometry. So that's a different technique. So basically now what we're going to look at is, again, the light of the star, but we're going to see that when a planet comes in front of the star, then because of the shadow of this planet, the luminosity of the star will drop just a little bit, okay? And what is interesting is that this drop in luminosity, will inform us on something else. Because, as I told you, radial velocity, it depends on the mass of the planet and its distance. So basically, if we get the radial velocity, we can get the mass of the planet. But we have no idea about the size of this planet. Now, here, this method is very complementary, because here we see that this drop in luminosity, it basically is proportional to the size of the area that the planet covers to the area of the whole star. And so, basically, this drop is just proportional to the radius of the planet divided by the radius of the star to the power of 2. So that's really interesting, because it means that here, if we know a bit the star, measuring the photometry will tell us the size now of the planet, not its mass. And if we can combine the two, it means that we're going to have size and mass, so we're going to have an information about density, which will tell us a lot about the composition of the planet, what it's made of, which is very important if we want to understand how it formed and if it's more like the Earth or more like Jupiter, for example. Now, the current precision with this technique is about a size contrast of about 10 to the minus 4, 10 to the minus 5. If we look again at numbers for Jupiter and the Earth around the Sun, the Earth is about 100 times smaller than the Sun. So in terms of area, it means that the contrast will be 10 to the minus 4. So it's barely detectable with this technique. And that's why actually we discovered, thanks to this, planets of the size of the Earth. Jupiter, is much bigger. It's 10 times bigger than the Earth, give or take. 10 times smaller than the Sun. So it means that the area ratio is about 1 in 1,000. 1 in 100, I mean. So basically, it means that Jupiter is much easier to find than an Earth. And we'll see that's why this technique, of course, detected a lot of big planets, but still could detect small planets like the Earth. So here, for example, is again the diagram from the first detection of a transit, which occurred in 1999, with a small 10 centimeter telescope from the ground. And you can see in the diagram that the normalized flux from the star as a function of time. And you see this drop in luminosity I was talking about. And they knew that it was a planet and not just some artifacts, because several days later they saw the same drop. And then later, again and again, we could see that there was a periodic drop in luminosity that is completely consistent with the planet coming in front of the star every time it orbits the star. But it's actually a bit more difficult, because you would like to know exactly. So we know already that transit gives us the radius of the planet. What we'd like to know is, can it give us exactly the period of the planet? Because if we know the period, it means that we know how much time it goes, how much time it takes for the planet to go around the star. But it also means, thanks to Kepler's law, that we can know what is the distance between the planet and the star. And that tells us a lot, because it means if we know a bit about the star, we can know what is the luminosity of the star, so we can know how much light the planet receives. So it gives us a lot of information on its temperature. And so that's why we would like to know the orbital period. So of course, if we had a magical observatory that could look at the star all the time, we would have what we call a light curve like this, where we'd see the luminosity of the star normalized to 1, and sometime we would see the transit and the dip in the luminosity. And as we already know, this dip tells us the size of the planet, and the period will tell us a lot. The problem is that if we are observing from the Earth, there is a problem with that, is that we don't have such a continuous light curve. Because basically, the light curve that we're going to have, in effect, is going to look like this. Why? Well, just because sometimes, there are clouds, you have to observe something else. You cannot just take all your equipment and observe the same star over and over again. But also simply because you cannot observe during the day. And so, by construction, you will have some unknown, you will have some gaps in your light curve. And then you have to decode these light curves, this segmented light curve, if you want to understand what is the period of the planet. So what you're going to do is, just like a Cluedo, you're going to try to guess what is the period, and then you're going to see whether it fits or not with your data. For example, I could say, okay, let's look at the first transit on the left, second transit. Let's say that this is the planetary orbital period. Then I'm going to try with the arrows, I'm going to just show where the transit should be if that was the period. And then I see that basically on the right of this diagram, I have one transit where there is not an arrow on top of it, meaning that this model doesn't work because it doesn't predict a transit where there is a transit in our data. So let's try something else. We see that on the right, we have two transits that are closer. Let's say that these are, this is the orbital period. And then we're going to do just the same exercise. We're going to look at the different locations where we predict transit and see if there is one. And we see here in the middle that there is another transit that is not explained by this model. So let's try again. We can just divide by 2 the period and do something like this and see if it works. Here, for example, if we look at the data, we see that we have transit where we have data and that and there is a transit where we have predicted it. There are some transits that are predicted in regions where we have gap in the data, so we cannot say anything, but we don't have anywhere where we have data where transit has been predicted and where we don't see a transit. So this could be a scenario that works. But we can still decrease the period and still do this. And here we see a limit because here you can see in several places where you would predict a transit, but the data shows that there is no transit. And so if we come back to the only solution that worked, and we actually show the original light curve, we see that this is actually the right scenario where, and now we have the right orbital period. So it's just to show you that when you work with exoplanets, if you want to learn about them, you'll have to decode some stuff because you cannot just go and look at it with your eyes. You have to look with very indirect information, and so you have to use physical laws to try to understand what is really going on in these systems. As I said, from the ground, it's very difficult, and it's also time-consuming because, like for radial velocity, you need to look at the stars one after another, and so it's very time-consuming in terms of telescope time. But fortunately, in 2006, we had a space mission called CORO on the French and European side. And then in 2009, there was the Kepler mission that launched a satellite that, whose mission was to actually stare at a field of stars for a very long time. And so here, for example, is the field of stars that Kepler looked at. That's the small rectangles. It's around the constellation of Cygnus. And so this spacecraft looked at this field for several years. And what is interesting is that in this field there are many stars. As you see here, you have the full CCD, and you have a zoom around the part, and you see all these dots are stars. And for each of these stars, what you can do is have actually a light curve. So you see, in time, they could monitor the brightness of all these stars, all these thousands and actually tens and hundreds of thousands of stars. And then they could discover the transit on this around all these stars that occurred during the mission. So here, for example, is a small animation where you're going to see the Kepler field. Each dot is going to be a transit. It's only showing 6 days of data. So each dot is a transit. The size of the dot tells you what is the size of the planet that transits. The color of the dot shows you what is the estimated temperature from the planet that is transiting, and that has been estimated, as I told you before, from the orbital period and knowing what is the luminosity of the star. And you can see that there are many, many objects that were discovered. And so we are only looking at a small patch of the sky, but that's how we discovered several thousands of planets. And so if we now look at all these planets, but in a different parameter space, again, I'm going to show you all the discoveries from Kepler. Actually, not all the discoveries. Here I'm going to show just what we call the multi-planet system, so planets where you have a star and at least 2 planets, and they are going to be to scale, in the sense that the dots are the size of planets. They are not to scale, but the size of the orbits is going to be to scale with the scale of the solar system that you can show here in the upper right. And so you see actually all these thousands of planets that we've discovered, and so they have a common property that just they are on very tiny orbits, and that's because there is a big bias still in this method, like in the radial velocity method. It's just because planets, they have a much bigger probability to transit if they are close to their host star. To give you an idea, if you take the Sun and the Earth, because the Earth could orbit like this, but it could as well orbit like this, it has only one chance in 200 to actually orbit, to be seen transiting from anywhere in the sky. And so that's why we discover many transiting planets that way, but we discover mostly planets that are on close orbits to the star. I showed you this image. For those who don't know, this is Kepler, and I think it's interesting because actually, thanks to this mission, we discovered a lot, but still, we are now, at the end of this mission, let's say, we were at the stage where Kepler was when he was looking at the solar system. So we know that there are planets. We know we have a good understanding of the probability of, how many planets there are around any single star in the sky. But we only know their mass, their radius, we know that they are there, but we don't know what they're made of. And now the question is, can we go further? Can we actually stop just doing detection of these planets and trying to characterize these planets? And what I mean by that is, for example, how can we know whether there is an atmosphere of this planet and what this atmosphere is made of? And so in the rest of this course, I'm going to try again to look at the tools that we use to actually infer whether there is an atmosphere or not on these planets. So how can we know that these planets have atmospheres? And again, we have to understand that we cannot go there and we cannot take a picture of it. So we are going to have to figure out ways to actually infer the presence of an atmosphere without having a photograph. The interesting thing is that objects with an atmosphere, it looks very different at different wavelengths. Why did I say very? It's, of course, without an atmosphere, even solid surface, they look a bit different at different wavelengths. But really, when you have an atmosphere, as you'll see here, the difference are enormous. So here, for example, this is a video from data from the Sun. And what you see here is that at different wavelength, each small section is a different wavelength. You see that the Sun looks dramatically different. And the reason for that is just that when you look at different wavelengths, because there are molecules against an atom in the atmosphere of these objects, these atoms and molecules, they do not absorb the light the same at different wavelengths. So meaning that the atmosphere, it can be more transparent or more opaque at different wavelengths. And the thing is that because of that, we see deeper regions of the atmosphere. For example, if we are in wavelength regions where the gas that is making up this atmosphere is more transparent. And then the corollary to that is that the flux that we receive is determined by the temperature of the region that we probe at this wavelength. And that's why if you look at the Sun here, there is a small schematic showing you what the Sun looks like at different wavelengths. So for example, from visible in the upper left to basically far ultraviolet in the lower right. And under each image, it is shown what is basically the region and the temperature of the region that is probed at these different wavelengths. And you see that here, when you look in the visible, basically, you see the Sun as we all see it with our own eyes, kind of yellow, and because it is the color that some object would have if it were at the temperature of the surface of the Sun, which is 5,000 kelvins, 5,000 degrees. But then, in the upper atmosphere of the Sun, the temperature, because of some phenomena, rises a lot. And so it goes from 5,000 Kelvin near the photosphere to actually 10,000 and even millions of kelvins in the chromosphere and in the really upper atmosphere, in the corona. And so that's why when you go towards the UV, the atmosphere is more and more opaque, and so you see regions that are really higher and higher in the atmosphere, and that's why you see this temperature that is increasing a lot. And that's how you probe the atmosphere of the sun. So that's how you probe the atmosphere of the sun. But for a planet, it's exactly the same. So if you look, for example, at our planets from afar, so you, again, because that's the game, we're not going to see a picture of the planet, we're just going to see a spectrum, which is the luminosity of the planet as a function of wavelength. We see that the brightness, the flux that we receive from the planets, it changes from a wavelength to another. And this is due to the various molecules that we have in the atmosphere. In particular, for example, here in the middle, you see that around 15 microns, we have this big dip in the spectra of all 3 planets in the solar system, so the Earth, Venus, and Mars. And this dip is due to CO2. Carbon dioxide is very opaque at 15 microns. So basically, it means that we see the upper atmosphere, and the upper atmosphere is much colder on all these planets than the surface, and that's why the flux here is much smaller. And if you look, for example, around 7 or 8 microns, you see that the atmosphere is much more transparent. That's why we see a higher flux. And so for the Earth, for example, we see flux that's coming close to from the surface. That's why the flux is higher. But still, we can make a difference, and that's how we can now get a picture of what is inside the thermal structure of this atmosphere, because we see that even in this region, we see that the flux from Mars is much smaller than the flux from the Earth, and that's because Mars is much colder than the Earth. And so that's how we can, for example, know what is the thermal structure, what is the composition of the atmosphere in our solar system from remote observations. But the problem is that this requires to be able to distinguish the photons from the planet from the photons from the star. And we already saw in the beginning that it's very difficult. Actually, what we're going to do is we're not going to try to resolve spatially the planet from the star. We're going to use a different technique where we're actually going to use time to isolate the planetary photons. How are we going to do that? Well, as I told you, we are looking at transiting planets here. So these planets, they orbit around the star. And so we see here on the bottom what is the luminosity of the star plus planet system as a function of time, as a function when the planet orbits around the star. We see really on the lower part the transit. So when the planet comes in front of the star, the luminosity of the whole system goes down. And then the planet goes out of transit. We see the light goes up again. But when the orbit progresses, we see that the luminosity increases a little bit, because we kind of see at the end of the transit we were seeing the night side of the planet, but when the planet is actually going towards the other side of the star, we're going to see the day side of the planet, which emits more light. And then when the planet is going to go behind the star, we're going to have what we call an eclipse, and then we have a small dip. And this dip is actually the luminosity of the planet that just disappears behind the star. So now, at this precise point, we have a reference point because we have exactly the luminosity of the star alone. And that will be very important, because now, if we have this reference point, we can really know at each point in the orbit what is the light that is coming from the planet. And if I show you the first data set that used this technique from Knudsen in 2007, that's for the planet that is called HD 189733b. That's a hot Jupiter. That's one of the hot Jupiter that orbits one of the brightest stars in the sky. That's why it's been studied many times, because the transit and the eclipse are really easy to see. And what you see in the diagram on the right is, as a function of time or orbital phase, the luminosity of the system star plus planet that is normalized to the luminosity of the star. So meaning that when there is only the star in view, then the flux is 1. So we have on the left the transit. We have a big dip in luminosity. Then we have the luminosity of the star plus the planet that is seen zoomed in on the bottom panel. And you see that the light from the planet, it increases as a function of time. As I said, it's because we now see progressively more and more the day side of the planet. And then when, during the eclipse on the right, you see that the light from the planet disappears because the planet disappears behind the star. And we have this reference point when we have only the side, only the luminosity of the star. So again, now what we can measure, thanks to the fact that we know when the planet is in front of us, behind the star, or at which phase it is, we can measure the luminosity of the night side, of the left, of the day side, near the eclipse, and we know exactly what is the distribution of the flux from the planet. What is interesting here is that we can notice that the night side flux is non-zero, meaning that the flux when the planet is really near transit is not exactly the same as the flux of the star alone. And that is really important because if we had the planet without an atmosphere, the night side of this planet, it should be very, very cold. And we should not see any light emitted from this surface. So it means that there is an atmosphere on this planet. Of course, it was not a big discovery because we think this planet, which is massive, is like Saturn or Jupiter. So we did not anticipate that this planet would not have an atmosphere. But this tells us how we can infer whether or not there is an atmosphere on a planet for which we see the phase curve as we see here. And we see it right now. What is important, of course, is that this flux from the planet, especially if we're in the infrared, well, it's proportional to the ratio of the size of the area of the planet to the area of the star. So that's basically the transit depth, times the ratio of the luminosity of the surface of the planet to the luminosity of the surface of the star. Meaning that when we measure this planet flux, we can get an idea of the ratio of the planet to star flux, as we see. So, indeed, if we show this planet to star flux ratio as a function of wavelength for a very simple model of a planet, a black body, we can see here on the top the red curve is the flux that would have the hot Jupiter would have as a function of wavelength. And so we see that this contrast is well within range of the current instrument that we have. Again, we said that the range, the current precision for this kind of measurement is 10 to the minus 4, 10 to the minus 5. And indeed, if you look at HST that is able to look nowadays up to 2 micron, and Spitzer that, well, before it was decommissioned, had channels that went up to 5 microns, you can see that the planet to star flux ratio contrast is well within range of the instrument for hot Jupiters. Now if you look at a warm Jupiter, you see that this curve is going down and it's moved toward the right, and it's because as we go to cooler objects, the flux emitted by the planet is going to go toward longer wavelength and it's going to decrease. And so that's why we cannot, with the current instrument, look at a warm Jupiter, again, if it's around the sun, because here we are comparing we take the sun as a reference for the star. And of course, if we look at the Earth around the sun, again, we see that the contrast we need to attain is also much smaller. So here it's not 10 to the minus 10 as we have seen in the previous part, but here it's because we look at in the infrared and not in the visible. In the visible, again, the contrast would be even bigger. There is something that is really interesting, is that you don't have to look at planets that are around the sun necessarily. You can look at planets that are around other stars. And of course, if you pick smaller stars, like M dwarfs, well, here you see that the size is smaller, but even the flux, because these stars are cooler, so their flux is much smaller. And you see here that the difference in flux between a planet, let's say like the Earth, and the brightness of an M dwarf in the infrared is much smaller than it was compared to the sun. And that's why it's really easier to look at planets around these smaller stars. And if we could go even further and try to look for planets around what we call brown dwarfs, and the contrast would be even better, but we didn't find yet planets around this object, even though we think that there must be. It's just that we don't have enough capabilities to detect these planets right now. But the other thing that you can do if you want to look at a planet with this technique is just pick also a planet that is either bigger or a bit hotter than the Earth. And for example, that's what they did with this planet, which is basically a hot 1.3 Earth radius planet around a 0.6 solar radius star. So it's basically an M dwarf. And again, they looked at this phase curve, exactly the same that what we did before. So you see the luminosity of the planet per star system divided by the luminosity of the star. So 100% means only the luminosity of the star. And you see this dip, so they can measure the emission from the day side of the planet that is around 1000 Kelvin. But what is interesting here compared to what we saw before is that if you look on the left part around the transit, the flux from the star plus planet system is about the same as the flux for the star alone. And this means that basically here we think that there is no atmosphere or no thick atmosphere around this planet, and which means that the night side of this planet is effectively very cold. So that was the first, actually, I think, hint of saying that a terrestrial planet, a small terrestrial planet, didn't have atmosphere, which again is not unexpected, but it's really difficult to prove for an exoplanet. If we come back to a planet with an atmosphere, now we can try to answer a different question, which is, if there is an atmosphere, how can we measure its composition? So now we have to go a bit deeper into this. The thing, as I said, for our planets seen from afar, like the Earth, Mars, what was really important is we needed to detect, to know what was the brightness of the planet at different wavelengths. Here what we looked at is only at a given wavelength. We look at the system and we look at what is the evolution of the luminosity with time. So we can still try to use this time information, but now we're going to use it at different wavelengths. So what we're going to do is just look at the eclipse, so this small dip, and we're going to try to see how deep is this deep as a function of wavelength. And that's translated here. As you can see, you have several transits that are taken at the same time with an instrument, a spectrograph that is able to look at it in different wavelengths. And when we compute the depth of each of these transits at different wavelengths, we can infer this. So this is a spectrum that tells you basically what is the planet to star flux ratio, but as a function of wavelength. And here we have a spectrum which is just like what we had for a planet in the solar system, except that, well, of course, it's integrated over the whole planet. And here we can start to have information about what is inside these planets, because we see some features, spectral features, that are very much alike what we see in our planets. For example, here, in the middle, we see a dip, which is due to the water. We know that at this wavelength, water is very opaque. That's why we see higher in the atmosphere, and so the flux, if we have an atmosphere whose temperature decreases with height, the flux in this wavelength region should be smaller than in the region around it, and that's why we know from this data that there is water in these planets, water vapor. Of course, I'm talking here about hot Jupiters, so when I talk about water, you have to understand that I'm not talking about liquid water, but really about water vapor that is at temperatures of several hundreds of degrees, or if not thousands. The problem is that this technique of eclipses is very difficult, because eclipses are very faint, because they rely on the very high emission from the planet. The problem is that the thermal emission of the planet is scarce as the temperature of the planet to the fourth, and especially when you're looking at it with instruments that can go only at 5 microns, because nowadays the only data we had were from HST and Spitzer and goes only to 5 microns. We cannot go at a longer wavelength. So it's really difficult to apply these methods to many planets. And that's why actually, although it provides a lot of information, this eclipse spectroscopy is only applied to a handful of planets. But as we see here, there is small dip from the eclipse on the right, but the dip of the transit is much bigger. And it's normal that it's bigger because basically now we're not looking at the emission of the planet, we're looking at the emission from the star, which is much brighter, that is blocked by the planet. So the question is, could we use this transit to actually infer something from the atmosphere? And the answer is yes, we can. As you can see here, for example, this is a photograph from the beginning of a transit of Venus, and we already see a small rim around the planet that is due to light refracted by the atmosphere, light from the sun coming now towards us. So this is not how we're going to do it, because of course, as I told you, we're not able to image these exoplanets the same way than we do here. So we're not going to be able to extract just the photons that are coming from this atmosphere. So the question is, how are we going to do it? But this shows that there is indeed light that goes through the atmospheres and comes back to us. And the question is, how can we get the information? How can we extract this light? Here is another example. This is an example of Titan coming in front of Saturn. And you also see the rim around the planet is a bit more opaque in places. And it's actually here not because of molecules, but because of cloud particles in the atmosphere. But that shows you that the atmosphere at different wavelengths and different places can look a bit more opaque or a bit less opaque. And that's what we're going to use during the transit. How are we going to use that? Well, here again it's a picture of Titan to just show you the principle. If we look at the color, let's say the color of the surface of Titan, well, basically we're going to have a look at the transit and the size of the planet will appear a certain way, and so we're going to have this transit. But if we look at a wavelength, for example, in the blue or in the UV, where we see, because of the color of the haze there, that the atmosphere is going to be a bit more opaque in this wavelength, well, of course, the size of the planet will look a bit bigger in this wavelength. And that's why this difference in the depth of the transit as a function of wavelength is just going to be the signal that there is an atmosphere. And what is interesting is that the size of this signal, it scales like the transit depth times a factor which is just basically the height of the atmosphere divided by the radius of the planet. What is interesting is that this height of the atmosphere is basically proportional to the temperature of the atmosphere divided by the mean molecular weight and the gravity. Here, what is really interesting is that the scaling is not temperature to the fourth power as it was for eclipse. Here it's just temperature. And so it means that from one planet to the other, it's going to vary much less. And that's why this technique actually allows us to probe atmosphere of planets, even if they are much cooler than what we did for hot Jupiters. Because even if you look at the numbers for hot Jupiter, basically transit depth is about 1%, and the atmospheric signal is going to be about 10 to 100 times smaller than that. And so indeed, if we do exactly that, so we take transit at different wavelengths. So here, again, this was for eclipses. Now I'm just going to look at transit, and I'm going to find again a spectrum, that is the spectrum on the bottom right, where I see just the size of the planet as a function of wavelength. And here again, I see some patterns that are linked to the molecules that are inside the atmosphere. So what is funny is that you can see that actually it looks like a reverse spectrum from the others. And it's just because basically on the top, when you were looking at the emission, when there was water, it meant that you were seeing higher in the atmosphere, so lower temperatures, so lower flux. Here, if we're in a region where water is very opaque, it means that the size, the apparent size of the planet is bigger. And that's why you see that when there is water, you will have a peak in what we call the opacity, the transmission of the atmosphere. And so that's how you can actually, from the deep and through of these curves, of these transit spectra, you can infer the presence of different molecules. So here, for example, is just to show you that this has been applied to many planets. Here is just an example for 30 hot and warm Jupiters and some Neptunes actually, where we have looked at the Hubble WFC3 instrument that shows you basically the water band, and that shows you from the top left where you have the most robust detection of water to the bottom right where we have planets where we don't see water. Doesn't mean that it's not there, but it's maybe covered by clouds or other things that do not allow us to see the water. Well, of course, this is very much focused on water because this instrument is very well used, but mostly sees water. But it doesn't mean that it's the only thing that we have in these planets, in these atmospheres. So here is actually a spectrum that uses a lot of information from different, a spectrum that sees information from different instruments. So we have, for example, here in the middle, so it's still the same Hubble data. On the left, we have data from the Hubble's TIS instrument that is looking more in the UV. And on the right, you have data, the 2 points, or data from the Spitzer IRAC channels at 3.5 and 4.5 microns. And here, within this data, you can see a lot of high and through, and this tells you that this atmosphere is made up of different components. So you have water, of course. The Spitzer data tells us about possible presence of CO2. And in the UV part, you can see, for example, two dots that are very high, which shows us that in this very high atmosphere, we actually have atomic sodium and potassium species. So that's very well. The problem with this kind of spectra is that even though we are able to detect some molecules, it's really difficult to have robust determination of the precise abundances. And the reason is that because we're using data from different instruments, it's really difficult to stitch them all together. And so that's why it's really difficult to combine them in a very robust way. And for example, if you see the reduction of the same data by different teams, you see that the results are not exactly quantitatively exactly the same. And so that's why I think it's really important to remember that even though we now start to have information about the composition of these atmospheres, there is a lot of uncertainty about this, and so it's going to really look differently, I think, in several years. Now, just to try to see, can we do that also for much smaller planets than just Jupiters and Neptunes? And if you look at the numbers for the Earth, of course that's the same. The Earth has a much smaller transit depth. The atmospheric signal, 10 to the minus 6, is very small, and it's impossible to detect at the moment. But again, we do not necessarily need to look for Earths around the Sun. We can look for planets around smaller stars, and you can see here that, again, it's even for transits, it's really good, just because the size ratio of a planet is always much bigger if you look around a smaller star, but also because around a smaller star at a given temperature for the planet will transit much more often in front of its star, so it means that you can repeat observations much more often, and so you can have a much smaller noise in your data. And indeed, using this, we were able, for example, here to detect water in a small planet. Here it's K2-18b. It's a planet that has been discovered by K2, the follow-up mission from Kepler. And that's a temperate subneptune. It's about, I think, 300K or 250K for the atmosphere. But the planet is a bit bigger than the Earth. It's about 2 Earth radii, so it's really a mini Neptune. It's orbiting a small M dwarf. And so what is interesting here is that this spectrum shows us the presence of water. And that was actually very interesting because that was the first detection of water for a planet that was as cold and cold enough maybe to have actually water clouds in the atmosphere. This still points to the fact that this atmosphere is dominated by hydrogen. And so it means that it's not really what we would think as a terrestrial Earth analog. It's really more like a small Neptunes that is cold enough to have water vapor and maybe water clouds. Although in later studies, it's been shown that maybe actually what we call these water features might actually be due to methane. And if you want to go even smaller and really look at terrestrial planets, to show you that in transit it's possible, even though it's very difficult, thanks to the fact that we discovered back in 2019 the TRAPPIST system, where we really have Earth-like planets around the smaller stars in the galaxy, so meaning the smallest M dwarfs, like TRAPPIST. And after that, we actually applied to have time on the Hubble telescope to try to take transit spectra of these planets. And that's the result you see here for 4 of the planets. And what you see is the problem that if these planets had, like K218 that I just showed you, an atmosphere of hydrogen and helium, then if there were water there, we would have detected it. And that's the kind of the lines that you see, the blue lines or the clear lines, the models behind it. And you see that the data, the dots, they do not follow this line. So meaning that actually we think what is happening here is that basically these planets, they just don't have a hydrogen-dominated atmosphere. We don't know actually if they have an atmosphere. Now that's what we want to know. And for this, we need to look at these objects with bigger telescopes, basically, to be able to reduce the noise on this observation and trying to make the difference between the curve that we see in the middle of each plot that basically would tell us whether there is no atmosphere or much more like a terrestrial atmosphere, maybe N2 dominated, or a steam atmosphere, water dominated. And that would really tell us what is inside these atmospheres. So what next? Basically, well, I could not go away without telling you just a little bit about the James Webb Space Telescope, which is the descendant, basically the replacement for Hubble. Just to give you an idea, this illustration shows you to scale the size of the JWST mirror compared to the size of the Hubble mirror. And so that really shows you that in terms of the capacity of this observatory to look at these objects, the quality of the data will be much, much better. Just because the collecting area will be much bigger, so the noise, the photon noise will be much lower. But it's not the only thing. The really important thing is that also this observatory is actually going to much longer wavelength. So it means that we're not going to be constrained only with data to 5 microns, because of course Spitzer in the beginning was meant to look at 100 microns, but when we really started to use it for exoplanets, it was near the end of its mission, and we could only use some modes, some instruments that could go up to 5 microns. So that's why when we're going to open up these mid-infrared regions, we're going to be able to look at much more planets. But we just have to remember that this James Webb Space Telescope is not a dedicated instrument for exoplanets, because it's going to do a lot of other stuff, like stellar characterization of stellar evolution, characterization of galaxy cosmology. And so when you look at the number of objects that this telescope is going to be able to look at, it's not that big. And that's why, for example, we also in Europe, we have pushed to have another mission, which is the Radial mission. And you see a prototype here that is designed to be launched in the end of the 2030, well, the end of the 2020 time frame. And here, what we're going to do is have a much smaller telescope, but it's going to be dedicated to look only at planets for 5 years. And the idea is to survey 1,000 of exoplanets with varying radii and planetary temperatures, so that we can really map out what is the diversity of the atmospheres. And just to end, I just want to mention what I did not talk about actually, which is high resolution spectroscopy that is done right now, for example, with the VLT, and that's going to have a big push when we're going to be able to use the ELT, which is the extremely large telescope that is going to be put online in a few years. It's not because it's not an interesting technique, because actually high-resolution spectroscopy can do things that are very complementary to what I talked about. It's just that, well, it would take a lot more time to go into the details of that, but just want to mention that if you're interested, there is a lot more to learn and a lot more that will be done thanks to these observatories. And with that, I will thank you.